Hello and welcome to the Cambridge Skeptics live stream. The Cambridge Skeptics are a volunteer organization and we are dedicated to promoting critical thinking, science, and positive skepticism in our local community of Cambridge, but also across the UK and beyond. And this week, we have a very special guest joining us. Tom Kerss is an astronomer and author of several books on astronomy, including most recently, Northern Lights, the Definitive Guide to Auroras. And so Tom is here to tell us not just about his new books, but also about space and how we know it's real. Tom, take it away.
How do we know? How do we know it's real? Wow, that's so nice of you to show all of my books. Actually, I'm not going to talk about my books because it's self-serving.
They're no good. What?
Yeah, they're rubbish. You can read the reviews and find out. There is a review on one of my books. Stargazing is the name of the book, and one of the Amazon reviews says it doesn't slide very well on carpet. 3 out of 5. That's my favorite review.
It's correct.
It's correct. It's comprehensive, and it gets straight to what's important about a book. So I can talk to you about space, however.
I'd like to talk about
that review, that terrible review.
Friction of book covers. That's what I want to talk about.
Do you know what? As I will say this, as an author who obsessively checks their Amazon reviews for validation, it is quite frustrating when you find a review that's glowing, overflowing with positivity, and then it ends with 4 stars out of 5. So this book it changed my life. It saved my marriage. 4 stars.
It slid across the carpet beautifully.
It slid across the whole city and came back to me. 4 stars. And I think, what can I do? What can I add to get the perfect score here? What's missing from this book that's enlightened you and raised you to a new plane of understanding? I don't know. I don't understand. But then again, it's just a review. You can't take it to heart.
Yeah. And I'd love to know actually how you did save someone's marriage with astronomy. How could one do that?
I can't disclose the details.
Is this what you need to discuss a week before your marriage?
I'm putting the details in my next book, which is going to be called 50 Shades of Milky Way. And you can read that and find out all the gruesome details.
Amazing.
Right.
Space. Well, I come as an ambassador of space, although I'm fully aware that I'm with the perfect company to talk about space, because let's be honest, everyone here is a nerd, and space is the prime nerd subject. It is the beginning, the alpha and the omega of all nerdness, because astronomy is the oldest natural science. I think that's what gives it the authority to step in and be like, we're going to make all the coolest shows. We're going to have Star Trek, and you're never going to get a biological version of Star Trek or a chemistry version of Star Trek that's as good. Sorry, it's a space show. And as a space person who studies space and makes money out of space, I'm here to represent space and try to give space a good name in the skeptical community, because there's a lot of misinformation about space. Actually, more misinformation than there has ever been. Most of which comes from places like Facebook, which in my view is, maybe somebody's tuning in from Facebook. I don't know, but I think Facebook is kind of a net evil in the world. But I remember the good old days before misinformation online, when you had things like Microsoft Encarta, which was curated by people. And so it had really good information in it. And it was things like Microsoft Encarta that made me want to know more about space. But now what's extraordinary is that we've never known so much about space in a way, but there's also never been so much mistrust in what we understand about space. Even hundreds of years ago, when space was arguably much more elusive and our lives were not as reliant on it, people had a greater trust for the understanding of space, probably because they were compelled to understand it. Whereas now I think we're living in an age where some people are compelled for some reason not to understand stuff, or to limit how their view of the world, or to repackage all the information they receive and put it into a pre-existing notion about how the world operates.
You mentioned that people had misconceptions about space on Facebook. What's an example of one that you're seeing?
Well, I know you talked about flat Earth theory. Flat Earth theory is pretty much exclusively an internet phenomenon. It wasn't a major there were no major advancements in flat Earth theory. It has been historically connected to some fringe religious figures in history, particularly in American history, but it never ever gained an audience until the internet existed, and it never gained a following. So that's a big one that exists. But I suppose the premium one that I get frustrated with is the idea that every scientific advancement, every little discovery, every little image of space is some sort of forgery in a giant game of scamming the public, in which NASA, which is made up of hundreds of thousands of people, the European Space Agency, ESA, which the UK is a part of, the Japanese Space Agency, JAXA, the Chinese Space Agency, the Russians, Space Forces, if all of these agencies together are trying to hoodwink the public with fake images of things on the surfaces of other worlds like comets and so on, and then make up all these stories about finding interesting chemical elements here and there, that is a difficult one to tackle. And that's absolutely on the rise. I've seen that happen, hugely surged in popularity in my lifetime. Basically, the idea that everything we learn about space is being forged for the purpose of, well, for some reason I can't understand. Do you understand? Does anyone understand? Why?
How do we know it's not being forged? How can we know things about space reliably?
We have to make a big argument from authority and say NASA isn't lying. It's all true. That is a really good question. I think that space is actually, as a science that you can do yourself, it's one of the most accessible, even more so than chemistry. You can buy a chemistry set and do chemistry at home, and that's a great gift for a kid with a curious scientific mind. But you don't need anything to begin exploring space. You can just start stargazing, and you don't even need a good clear dark sky. You can live in the city, which about half the world's population now does live in urban spoiled skies, and you can just study the moon. You can literally study the phases of the moon, and you can start to grapple something that ancient people took centuries to figure out, the idea that the moon is orbiting around the Earth, which you can measure yourself using just your eyes and maybe a sketchbook and a calendar, so a piece of paper and a pencil, and you can recreate that ancient knowledge yourself. And nobody can stop you doing that. Nobody can sweep in and say, stop learning about space. You might uncover something. And if you...
That's the question I wanted to ask. At what point in your training, if this had all been fake, would it have been necessary to bring you into the conspiracy?
Me personally,
yeah,
as a very important individual, it all hinges on me, really. I'm the one that has to sell it. No, I have no idea. I mean, the thing is,
at what point would you have realized it was fake?
Yeah. At what point would I have realized? Well, if space is fake, when would I have realized it's fake? I think I would have realized when I was about 9 years old, when I was using my first telescope. Honestly, I would, because, okay, so I've got a telescope here, right, for demonstration purposes. This is a very dinky little telescope. And this is let me take the thing out the back. So at the front of this telescope is a lens, which is about 7 centimeters wide. And at the back of the telescope is just an empty aperture. So you can see that there's nothing inside the telescope. There's no holographic projector. There's no image inside. And although this telescope is modern, and it's made with modern components, it's made out of aluminium, and it's all machined, it's all fancy and so on, functionally, it's no different from the very first astronomical telescope, which we credit really to being made by a Dutch lens maker, Hans Lippershey, in 1608. Although actually the first use of an astronomical telescope, as far as we know, for the purposes of looking at the night sky, is by an English astronomer called Thomas Harriot in the middle part of 1609, probably July, maybe the first month, from southwest London. And then a few months later, very famously, Galileo makes the telescope, the popularity of the telescope explode, because although Harriot beat him to it, his studies were much more expansive in this field. So there's nothing functionally different about a telescope that you can buy and a telescope that existed hundreds of years ago. And I find it really magical. There's something, I think, magic about a telescope, because the glass is see-through, it's transparent, so you don't see it at all. And I just think it's beautiful that it's something that's basically invisible to our eyes actually makes visible so much more when you point it at the sky. So the way the telescope works is aperture at the front gathers light in much the same way as the aperture, the hole in your eye, gathers light, but it gathers much more light than the hole in your eye. That light is then focused towards the back of the tube. So you have far more light in a smaller image at the back. And then that image is then refocused into your eye using an eye lens or an eyepiece at the back. You can achieve from the ground functionally magnifications up to about 200 times from most parts of the world on an average night. I've been in the desert in Namibia and used the telescope at 700 times and it held up because there was no humidity in the air. And if it's very lousy seeing conditions, then you might be restricted to 100 times. But that doesn't matter. If you can get up to about 50 times, which actually some pairs of binoculars can do, you can see the rings of Saturn yourself, just like Galileo did in 1610. You can see the phases of Venus, which Galileo saw in 1610 as well. And you can see the moons of Jupiter. And all three of these observations basically take us away from the idea of the world, the Earth, being a unique platform and the light in the sky being holes on a giant sphere or little projections or something. Because at this point, you're now basically have a big perspective shift. You're basically seeing other worlds from the third person in much the same way as robots on Mars are now looking at the Earth from a great distance. And when I was 9, I was doing stuff like that. And then I was learning about the possibility of watching one of Jupiter's moons cast a shadow on Jupiter. And I remember reading in a magazine called Astronomy Now, which is still published, which I've had the great pleasure of writing for on occasion as an adult, that you can predict when this is going to happen. And I thought it was unbelievable that you could know when a moon was going to cast a shadow on another planet with that precision. And then I would go out and see it for myself. And that's the kind of thing that engenders a lot of respect in the understanding of the night sky, because you know that it takes a lot of thought to be able to predict something happening millions of miles away. Now, of course, you have to believe it's happening millions of miles away. But if it's not, if it's happening just above your head, or if it's some sort of holographic projection, then every single person in Astronomy Now has to be somehow in on this projection. They have to be receiving information from whoever's creating the fake image of the planet, telling them when the fake transit of the moon is going to occur and cast a shadow on the surface of Jupiter's cloud tops, basically. And that's becomes a much, much bigger conspiracy than just, NASA didn't go to the moon. It becomes every single expert in astronomy that watches the sky out of interest or for a living is collectively trying to fool everyone who doesn't do that.
And every amateur astronomer as well.
Exactly. And that's where the fine line is. And it's actually a big fine line, is the amateur astronomy community, because these are people that have no vested interest in lying about the universe. And also, they have unrestricted access to observe the sky themselves. There's basically nothing can stop them from doing it. Nobody can stop you from looking at the sky, whether it's as simple as looking at the moon, whether it's simple as looking through a telescope. No, then there's nothing that can stop the sky from reaching out to you either. So I've got another couple of props here. This is, I'll see if I can get my camera to focus. Maybe if I put my hand here. So This is actually a piece of rock that has come from the asteroid belt. This is a meteorite fragment. And this one was observed to fall. This one landed on Earth. People saw it coming down through the sky as a meteor, which is the bit that we see in the sky. And then the bit that lands on the ground, which is the meteorite, was later recovered from the location where it was assumed to have fallen. It fell some miles away from the observers, and they realized that it had fallen somewhere. And so the next day, they sent out teams of people to scour the desert in North Africa, and they identified the pieces in the ground. This one is another one. I'm really proud of this one, but this one is going to be hard to focus on. Let's see if I can get my camera to focus here. This is really tiny, and I don't think I can get any closer. The lens has a kind of limit. It's actually in a dab of glue, but there's a little fragment in there, and that is a piece of the moon, no less. That's actually a lunar meteorite sample. So that has come from a part of the moon. It wasn't collected by an astronaut. It just fell naturally to Earth as a meteorite. And it was chipped off the moon in a large collision when something crashed into the moon, just knocked stuff off the surface. The gravity on the moon is low, so the escape velocity is quite low. So material from the moon can quite easily escape into space, find its way to the Earth. These rocks have been studied. So I'm trusting a scientific authority that's told me why these rocks come from space. But the logic the first principles are straightforward. We know they've come from space because they are chemically completely different from the kind of rock that we find on the surface of the Earth. Not completely different in that they're not made from the same elements, but the abundances of those elements are completely different. And we can know what the abundances of the elements are on the moon without even going there. We can just look at sunlight being reflected off the moon, and we can use that reflectance, that mineral reflectance factor, to figure out what's on the surface of the moon. And we can match the profile of moon rock to samples that we have on the Earth. This is something that, of course, is a little bit further out of reach for the average person, but it's still possible. You can find out what's inside a piece of rock using a spectrometer. Now, it's expensive, but if you really believe that NASA is lying about bringing samples back from the moon, you don't need to go through NASA to prove that. You can save up the money collectively as an organization, buy a spectrometer, get hold of a sample of supposed moon rock, and test it and prove that it comes from the Earth. Nobody's doing that, but it can be done. So in my view, although space seems very far away and it seems like an expensive and inaccessible science, it starts very simply, and there are many, many routes to proving that it's incorrect. And in many ways, I think this is cheaper than trying to find what was it Richard Dawkins said, like a fossilized rabbit in the Precambrian era, basically trying to find a fossil of an advanced life form hundreds of millions of years ago. That would be expensive and difficult to try and do. You'd have to scour the entire surface of the Earth, but you only need a spectrometer and a single sample of supposed space rock to knock down the idea that rocks fall from space at all. And of course, rocks fall from space and are picked up by amateurs all the time. And that happened with the Winchcombe meteorite recently in the UK. And they took it to the Natural History Museum where it was tested. Is the Natural History Museum also lying? Are they also in bed with NASA on this issue? Maybe, but I doubt it.
And the thing is, we know that the chemistry of everything that falls from space is weird compared to everything that we've ever measured on Earth. I remember I was measuring strontium isotope ratios once in an archaeological context, and we were trying to get the chemistry of our experiment working correctly, and we clearly messed up because we got the results back, and it was like, yeah, unless this is from the moon, you've done something wrong. And obviously it wasn't from the moon, and we worked out what had gone wrong in our lab processes. But I wanted to ask you about when you talk about being able to trust the evidence from astronomers. I'm guessing that light is your primary source of evidence, and I was wondering if you could talk a little bit about different ways in which you can use light as evidence. Because you talked about mineral reflectance, you talked about spectroscopy. What else is there that you can use?
It's a really good point to bring up light, because I vividly remember as an undergrad astrophysics student at Exeter going into a lecture one day quite early on in my first year of study, and having one of our professors there just walk out and confidently ask everybody in the room, is astronomy even really a science? Is it even really a science? And everybody was like, yeah, I wouldn't be here if it wasn't a science, right? I'm into science and I picked this degree. But it's a valid question. It's actually a really good question, because in science, one of the things that's crucial to modern science is the principle of experiment, and the idea that if something disagrees with experiment, then it's invalid scientifically and needs to be reinvestigated. And in astronomy, there are very few experiments that you can actually perform. You cannot take a sample of a star. You cannot take a sample of an exoplanet. You can't even take a sample of Pluto and get it back to Earth. It's way out of our energy budget to achieve something like that. But what you can do is you can intercept the light that's falling on the Earth from space, some of which you can see, turns out most of which you can't see, but you can build machines that can see it for you. And that light becomes your sample. So the question is, what kind of experiments can you do on it to determine that, well, for one thing, that it's come from another place, and for another thing, that that it can teach you anything at all. And what I love about spectroscopy of all things is just how much information there is in light, embedded in light. So using spectroscopy, which, for the benefit of anyone who's listening, spectroscopy it's like making rainbows for a living. You basically split light up into its component colors and you study them. Pretty cool job, I think. And spectroscopy is the study of color as it pertains to light. And light information is so diverse. There are so many things that can be encoded in a piece of light. So one of the most notable things is basically the electronic structure of something that the light has interacted with. So if light has bounced off the surface of a mineral, the electronic structure of that mineral will alter in some form the color of the light. You might not even notice the color has changed, but a spectrogram can show you how the color has changed. It can show you certain colors have disappeared, for example, because they've been absorbed by the minerals in that light, whereas other colors have been preferentially reflected. Spectroscopy, as it pertains to astronomy, is practically the most useful tool that we have. And it's no surprise that most of the telescopes being built today to go into space particularly are actually being designed to look at wavelengths of light that we can't see, because we're not as interested in photometry and the brightness of things so much as we are in spectroscopy and the color of things, because that's where the really good stuff is to be learned. Perhaps my favorite example of how spectroscopy encodes information is in the expansion of the universe. We know that the universe is expanding because light from objects that are distant is redshifted. It's been made to be more red, meaning that its wavelength has been elongated, its energy has been lowered, and we interpret this as the change in the scale of space itself, and the waves, if you will, or rays of light, basically adjusting their wavelength to fit the amount of space that they formed in as space changes size. So the universe is expanding, meaning quite literally a meter is getting longer. Like the concept of a meter, if you fixed it at any given time in universal history, it will be longer in the present. And light has to obey the stretching of the space that it occupies, and that lengthens its wavelength. Now, you could say, if you were skeptical about that, you could say, well, how do we know that galaxies that are really far away aren't just full of red stars? How do we know they're not just red? And the answer is spectroscopy, because when the light is generated in the star, there's a color missing, which is called the hydrogen alpha absorption line. There are actually many colors missing, but H alpha is one of the strongest, and it's about 650 something. I want to say 656.2 nanometers. Somebody can probably check that, but it's a red color basically, and it gets absorbed by the hydrogen gas inside the atmosphere of the star, and the outer atmosphere particularly, which is a sort of extended envelope, a corona we call it, around the star. So when the light reaches us, the hydrogen alpha shadow is present, showing us that hydrogen is in the star where the light was generated. So we see this from sunlight as well. But here's the really cool thing. When the light leaves the star, the hydrogen alpha absorption happens. Then the light travels over great distances of space to reach us, and it's redshifted. And that corresponds to a change in the position of that shadow. That shadow's wavelength actually shifts further to the red, meaning that if you were to just analyze that spectroscopically, you'd have to say, well, hydrogen gas can't have absorbed that, because the absorption line for hydrogen gas is determined by the quantum electrodes, the quantum structure of the atom, and the singular hydrogen electron that typically binds with an atom. And so therefore, it has to be a different gas, but there is no gas responsible for that absorption profile. What's really happened is hydrogen has absorbed some of the color, and then as the light has traveled over space and been redshifted, that redshift has actually stretched the position of the hydrogen line. And that means we know that the light has changed its wavelength on its journey to us. So this is a good example of how we can extract information from light using instruments on the ground. Like basically the light is carrying information about its own history to us over sometimes billions of years of travel time.
And is this generally how you would know that something is, or this method is how you would know that a star is, say, smaller, closer and dimmer versus further, brighter and larger?
Talk about standard candles.
Standard candles. Love standard candles. Well, this is another good topic actually about how we know what we know about space. How can we trust redshift, for example, as a measure of distance? So redshift is a number. It's a dimensionless number. It's a ratio, and it's the ratio of the speed that something is traveling divided by the speed of light. So if a galaxy is measured to have a redshift that's receding from us at half the speed of light, actually redshift can exceed the speed of light.
Can I ask you a question about the expansion with redshift before you go on? So I was always taught that with the expansion of the universe, that it's not like the universe is accelerating away from us. It's just accelerating everywhere. It's like a cake with raisins in the oven, and all of the raisins like all get farther apart from everyone as the thing is growing in the oven. So like if I'm whatever raisin I am, I see all of the other raisins getting farther away from me. But what you said just now is when you said that it was the meter would also be changing. I guess what I hadn't realized is that it's not like, it sounds like what you're saying is all meters are equally, like no matter what the scale is, it's all expanding equally. Whereas for some reason I was thinking that it was the individual galaxies that were moving.
Yeah, that's what I thought.
Yeah, it's all the space is expanding between every galaxy. Think of it like distributing a bunch of ants on the surface of a balloon, and then blowing up the balloon. So every single ant moves away from every single other ant, but really the space between each ant, which is the balloon itself, is what's really expanding, and the ants are just being carried.
Are the atoms within the ant also getting farther away from each other?
They would, except that the interatomic forces bind them together at distances that are convenient for them. Exactly. So what that comes down to is that the expansion of the universe, which we call the Hubble flow, it has a certain force to it, a certain strength, and that strength is very great over a very great distance. It's sort of like the inverse of gravity. As some people have described, like dark energy as the inverse of gravity, in a way of thinking about it, not so much in a kind of physical model sense, because gravity acts, over great distances, whereas other forces tend to balance out. That's why we know that it's not electrostatic forces that bind galaxies together, it's gravity, because the electrostatic forces, once you get far enough from a galaxy, are kind of neutralized by the presence of all the various charged particles there. The dark energy factor, or the expansion of the universe, if you like, is essentially, if you imagine two people are two, let's say, a meter apart, and they're being pushed apart at a certain rate, a third person, I've got this the wrong way around on my screen, is being pushed apart at that rate as well. So from an observer on one side, someone twice as far away is moving away at twice the speed. So the Hubble constant, which is the speed, if you will, is actually given in kilometers per second per megaparsec. So it's a speed per distance. I can try and unpack that a little bit. So kilometers per second is a basic speed. The Hubble constant for the record is around 67 kilometers per second per megaparsec by latest measurement. So that means that for every megaparsec between two objects, they are receding from one another at 67 kilometers per second. A megaparsec is 1 million parsecs, and a parsec is about 3.3 light years approximately.
But the Millennium Falcon did the Kessel run in less than 12 parsecs.
In less than 12 parsecs. And then what they had to do in the Solo film, let's not get into new Star Wars, because that actually makes me very upset, is they had to basically retcon it, because they just can't leave things alone, so that it's like the computer made a more efficient calculation or something.
They turned it into a distance thing rather than the speed.
Well, it is a distance thing. They got it wrong.
They got it. George Lucas got it wrong, and we didn't mind, and then Disney got it right, and we hate it. It was fine when it was wrong, basically. Yeah, that's a good one. Actually, parsecs are relevant, because the way that we measure distance begins with parsecs. The way that we can measure distances to things that are nearby in the universe is by a method called parallax. And we kind of all familiar with parallax. When you put your fingers, one close to your face and one far away, and you move your head left and right, the thing that's closer to your face moves more quickly. The tree is going past the train window, rushing by, but the castle in the background is moving slowly, and the clouds are barely moving at all. And this principle is used to measure the distance to stars to a distance of about 100 light years or so. It's not really accurate beyond that, because the angles are so small. We use the motion of the Earth around the sun as our head wobble, going back and forward. And that takes, 6 months basically to go side to side. And we look at a star, and then we look at it 6 months later, and we see how its position has been displaced against much, much fainter stars, which we assume are much farther away. So as the nearby star wobbles a little bit, we can do a pretty simple bit of trigonometry. We can pretty much just say that the distance in parsecs is the inverse is 1 over the angle in a unit called arc seconds, because for very small angles, that's basically true. And that allows us to get the distance in parsecs, which we've measured to be about 3.3 light years. So then we have standard candles. Standard candles have a slightly different understanding about them. Standard candles are used understanding how the brightness of a star relates to its distance. And there are two ways to think about the brightness of the star. There's the apparent brightness, which is what we measure from the ground. This would be a photometric measurement, by the way. So we measure that precisely with a photometer that literally is counting the amount of light entering it and giving us a value. And then there's the absolute brightness of a star. And that is the apparent brightness from a fixed distance. So we can use a fairly straightforward conversion. If we know the absolute brightness of a star and we measure its apparent brightness, we can actually use that to measure its distance. So the way that standard candles work is that standard candles are types of stars for which the absolute brightness is known. And the way that the absolute brightness is known is that these stars vary in brightness, and the way that they vary in brightness is actually related to their absolute brightness by certain physical properties that came to be understood around the turn of the 20th century. So around that time, when people were beginning to understand how stars shine through nuclear fusion, it became possible to use the changing fusion rate to calculate the absolute magnitude or absolute brightness, we say, of a star. And then by measuring its apparent brightness, get a distance measurement to it. So that gives us the ability to measure the distances to stars that are much farther away. And quite famously, Edwin Hubble discovered a variable star in our neighboring galaxy, the Andromeda Galaxy. And at the time, nobody knew how far away the Andromeda Galaxy was, but Hubble used one standard candle to calculate that it was about 700,000 light years away, which at the time, in the 1930s, that was 10 times farther away than the next most distant object known at the time. So that really changed the way that we think about the size of the universe. Today, we actually know that the Andromeda Galaxy is about 2.5 million light years away. So Hubble was a little bit short, but his central idea was sound. So then we have this measurement for distances that goes out to millions of light years. And that's where the redshift idea comes into play, that we can figure out how far away something is by knowing how fast away it's moving from us, by measuring the redshift. And that redshift is just the ratio of the speed of the galaxy or whatever divided by the speed of light. So it's just a dimensionless number. We sometimes use the redshift to calculate the size of the universe, but when you hear somebody say a galaxy is 10 billion light years away, that's probably close, but what we can really say about it is it has a certain redshift, and it might be that future models of how we understand the size of the universe adjust how far away that is. But the redshift is something that is observed directly. The distance is something we calculate through various assumptions. So we now have these three factors. We've got parallax, lets us measure things to about 100 light years. Standard candles let us measure things to a few million light years. And then beyond that, we have to rely on redshift because we cannot see individual variable stars in galaxies that are hundreds of millions of light years away yet. Future telescopes, maybe. Not
it's
yet.
all light.
It's all light. But the question is, how can we really trust it? And the answer is remarkably simple. The answer is we just look at where these things overlap. We just find a standard candle that's 100 light years away, and we compare the distance we calculate with the parallax. Then we can look at a standard candle in a galaxy that's 5 or 6 million light years away, and we can compare that with the distance we measure through the redshift. And what we find is where these three scales of measurement overlap, and there is enough overlap here to build a catalog of data and analyze it, they agree really well. And so the agreement confidence is high, and that gives us the confidence to say, okay, well, now that we've moved on to something that's 100,000 light years away, we can't measure the parallax, but we know that the standard candles that do have a known parallax give us good confidence that the standard candles we see at a great distance are accurate, as long as we assume that the physics of the universe are the same everywhere, which is a very, very fundamental assumption in, basically in everything, in ontology, in physics, in chemistry, everything. And that's something that's going to be hard to prove. But, I'll let anybody that doesn't wish to trust that go ahead and just not trust that. You can trust that the laws of physics don't apply in the same way everywhere, but eventually that's going to be eroded by some future measurement.
It's like it's using one measurement to then confirm the next one and use the sort of just step up from there. It's like using a ruler to make sure that your tape measure works, and then your tape measure to make sure that.
Well, it's similar to what Erica was talking about a few weeks ago when we were talking about dating methods, how you use different dating methods to confirm other dating methods.
And it's so important to do so, because if you really want confidence in a measurement, the more proxies you have, the more confidence you have. And it's confidence that scientists are trying to achieve, not just because we're bitter and lonely and we have no social skills, but because we want scientific confidence in the validity of our understanding of the things that we're evaluating.
Well,
plus we love proving each other.
I was going to say, disproving each other is what scientists do. Like, that's our job.
Exactly. That's why if you ever go to conferences, there are physical fights because all this kind of like bickering online and in papers erupts into physical violence. I've seen it firsthand at astronomy conferences, but I'm not going to name names.
Wow.
I think astronomy is actually the most violent science, probably.
That never happened in archaeology.
That's good. That's really good.
I was at
Which
one
is good because the archaeologists have weapons.
Exactly.
I did have one professor stand up at the back of a conference when someone was talking about like, oh, this new cool chemistry thing to look at like milk proteins at the dawn of agriculture. And this old professor stood up and was like, but what really is the Neolithic anyways? And we were like, not relevant, sir.
In astronomy, we just have, we have physical fights, but then we don't advance anything unless we have a vote. That's very important. And the vote has to pass with about as narrow a margin as Brexit. And then we say, that's it, Pluto's not a planet anymore because 54% of people have decided. 46% can suck it because 54% have decided.
What side were you on?
Yeah, which side were you on?
Side am I on? I'm not obliged to say. I can remain mysterious. I can just let it play out. I'm on the Pluto is not a planet side personally. Well, here's the thing. The whole debate is about language. It's about classification. Pluto is fascinating. It's fascinating that we know anything at all about Pluto. It hasn't even completed one orbit since it was discovered. And we know precisely how long its orbit is because it's so well studied. And when I was a kid, Pluto was illustrations in a book. Nobody knew what the surface of Pluto looked like. Then we had these crummy Hubble pictures. I mean, I say crummy, they are wonderful, but they are exceptionally low resolution because Pluto has a very tiny angular size. And then in 2015, we had the flyby of the New Horizons spacecraft, and Alan Stern, the PI, a very nice person, was adamant that Pluto is a planet, and this is the moment to promote that. And he's American. My girlfriend's American, so I'm allowed to say this. Americans want Pluto to be a planet because it's the only planet they ever found, and they don't want us taking it away from them. And that's what it's all about. No, I'm just kidding. It's about classification, because the thing about Pluto is the discovery of Pluto is really important because it represents a turning point in again, it's another one of those scale discoveries like we talked about with Hubble. The solar system became a lot bigger with the discovery of Pluto, because Pluto's orbit has always been known to be weird. It's always been known to be a physically unusual object in the solar system. It has a very highly inclined orbit, sort of like a comet might have. And its distance between the sun and Pluto changes dramatically. Pluto actually crosses the threshold and comes inside the orbit of Neptune for a short while, but then it can be almost twice as far away. So its orbit is highly inclined, it's highly elliptical, and its behavior is suggestive of some more chaotic, unknown region beyond the realm of the planets. And because Pluto goes into that region, which we now have discovered so many things in, motivated by Pluto's discovery, no less, we can understand that Pluto's orbit is chaotic. It is uncertain. It passes through so much material that if you were to collect everything in the orbit of Pluto and put it on one side of the scale and put Pluto on the other side, Pluto would be only about 10% of the mass of everything that it shares its orbit with, whereas the Earth is about 1.5 million times the mass of everything that co-orbits with the Earth. So in those terms, it sort of makes sense to say that if a world has stabilized its neighborhood enough, then we call it a planet. And if it hasn't, then it's a dwarf planet. And the problem with the label dwarf planet is that people think that Pluto is too small. And it is, in the sense that there are physical reasons why Pluto hasn't cleared its neighborhood. It is because it's small. But that isn't the reason it's called a dwarf planet. There are granular reasons here which give Pluto that label. But what's interesting is that has sparked a debate about how we classify these objects in Pluto's neighborhood in a region we call the Kuiper Belt. Should we call them dwarf? Should we call more of them dwarf planets? Some of them are. There's an object between Mars and Jupiter called Ceres, which used to be considered an asteroid. That has now been promoted to be a dwarf planet because it is round, but it's also in a very chaotic region, and it shares its orbit with lots of other asteroids and things.
I was going to ask.
Yeah.
Like, my understanding is Pluto very far out, sort of about the same size as Ceres, a little bit larger, but about the same size, and quite dark. Like, it's got quite a low albedo. So why did we discover and decide that it was a planet and just go, yeah, Ceres, yeah.
Well, wasn't there a time when people thought Ceres was a planet?
Yeah, okay.
Yeah.
Sorry,
You're absolutely right, Erica. You're absolutely dead on.
I'm winning the astronomy quiz tonight.
Yeah. Well, planet is an old word. Planet is a label that kind of needs an update. Yeah, if you were to take the original meaning of planet which comes from Greek, from Asteres Planetae, the wandering stars, then the International Space Station is a planet, because that's a point of light that moves across the sky of its own will. So in theory, satellites are planets, but planet has come to have a different meaning an object that orbits the sun, and a significant object which is naturally occurring. But for a long time, actually for most of human history, our understanding of the night sky has declared that the sun and the moon are planets. And then the naked eye planets, Mercury, Venus, Mars, Jupiter, and Saturn, make up a total of 7 classical planets as they were known. And it's no accident that we have 7 days of the week, each of whom have a name connected to the planets. Today is Tuesday, which is Tia's Day. Tia is a Norse equivalent to Mars. Tomorrow would be Woden's Day, which is Mercury's day. Thor's Day for Jupiter. Freya Day for Friday is Venus. Saturn's Day, and finally Sunday and Monday for the sun and moon. So the 7 classical planets have a big cultural influence. When the telescope was invented, new worlds were discovered. Asteroids, asteroid just means star-like, aster for star. So asteroid of a star-like form. And the first asteroids to turn up, Ceres, Vesta, and Pallas, for example, were all held to be planets. According to that classical definition, the sun and the moon had their status revoked, but the asteroids actually gained this planetary status. Although, having said that, the very first asteroid which was Ceres, was discovered in 1801, and that is a couple of decades after, or over 10 years after, William Herschel and Caroline Herschel discovered and identified Uranus from a house in Bath here in the UK in 1781. So 20 years is the gap. So for 20 years, there actually were 7 planets, then the sun and the moon. And then after the asteroids were discovered, there was a time when even in the Royal Observatory's archives here in Greenwich, where I live, there were as many as 13 planets listed in the annual observations. Then the number of planets started to fall again when the concept of the asteroid was understood more plainly. And that came to be when photometry of asteroids showed that as they rotated, their brightness could change quite drastically. And that was telling us that they actually had a very irregular shape. And so not being very round or substantial in brightness, it seemed a bit ill-advised to consider them planets, because they clearly didn't have as much to teach us as the larger planets. And indeed, there were many moons being discovered that were more significant than many of these asteroids. I've forgotten what the question was. That's the problem, isn't it? I've actually forgotten where we were. So for that reason, the idea of planet as a word being updated, it really, the whole dwarf planet issue in 2006, which was unfortunately the year that New Horizons launched to go to Pluto, that whole issue, it kind of ties into how we define a planet. And the dwarf planet debate overtook the real issue, which was narrowing down the definition of a planet. That was done in the same vote, basically, that a planet is now officially an object that is round, which orbits the sun, and which has cleared its orbit of significant debris. And then we have dwarf planets. And then in other solar systems, we have exoplanets. And exoplanets are not planets or dwarf planets. Their status is unknown. They're extrasolar planets. So it's really just a labeling thing. But in real terms, these are all big bits of rock or gas orbiting stars. And in those terms, their similarities are kind of much more interesting than their differences.
Got a question from the chat. So asking, what do all these different planets teach us? What are they about the universe, I guess?
All these different planets, what do they teach us? Well, Neptune can tell you when you're going to make money. Saturn is the portent of ill fortune. So it teaches you when you're going to die, basically, in Indian astrology. What can the planets teach us? They teach us basically the same thing that any aspect of the universe teaches us, which is our common history, a history that goes way beyond the common biological history, which is itself obviously a fascinating story about how all life comes from a single, essentially, culture of cells somewhere in the ocean. We have a shared cosmological history with everything. The planets are the neighborhood of the Earth, and while the Earth is not sentient or anything, its history is unique and fascinating, and it is a member of a family. And how those planets came to be the way they are is part of the story of how the Earth came to be the way that it is. So the planets really are teaching us about, history. That's what they're teaching us, how the solar system formed, which gives us indications of how other solar systems formed. And that has implications for our understanding of the habitability of other solar systems and how common Earth-like planets might be, how extremophile life might survive and cling on planets that are actually quite different from the Earth. And ultimately, and this is a bit bleak, the planets are teaching us where we might make a home one day when the Earth is no longer suitable for us by our own actions, or because we are so stunningly successful that we survive 1 billion years and various things become impossible on Earth and we have to go somewhere else, which I hope is the outcome. So I suppose they teach us a lot of different things. That's a good question, actually. I've never really thought about it. They provide jobs for planetary scientists. What more do you want? These people need to get paid. They need to uncover mysteries that are completely esoteric and don't really affect our lives in an immediate way.
I think they teach us to be humble. That they teach us that we're not the center of the universe, that there was not a special purpose in creating us, and that we're just a lonely blue rock.
A lesson that took a really surprisingly long time to learn as well, as most people looked at, things in the sky moving and thought, how is this all going around the Earth? It's very strange, but it must be going around the Earth.
Obviously.
The whole idea of epicycles, which was the great failure of Tycho Brahe, that you needed to add little loops to the orbits of the other planets in order to explain how they were going around the Earth and somehow going backwards at certain times. And now we say in some sciences, I don't know if this has gone into archaeology, but the phrase adding epicycles usually just means making your theory needlessly complex to avoid admitting something that you don't want to admit.
I'm going to steal that.
Michelle has a follow-up question. Sorry, Sam, you go first.
No, well, I was just going to say I came, and it is related to Michelle's question, which is, there is the question about there being life out there and the fact we haven't found it yet, unless something's happened in the last couple of hours. We haven't noticed.
I'm just checking Twitter. No, it would definitely be trending. I think we're okay.
But one of the things that, within the sort of Drake equation is, how many stars are there? How many of those have planets and so on? And I have a faint recollection of basically sort of an early life of the solar system sort of run through, and actually that as a rule, generally speaking, the gas giants tend to form kind of further out from the star and then migrate inwards, or just clear all the rocky planets out or move them well outside of the Goldilocks zone. But that in our case, the particular sort of distance of Saturn and Jupiter meant Jupiter moved inwards and then Saturn just kind of like hauled it back. And they ended up, Jupiter moved inwards, then Saturn hauled it back, but they kind of both moved to sort of roughly their current position. And actually what that did is it allowed the rocky planets to form in the center, in the habitable zone, but that's probably relatively rare, and presumably we can't have learnt that without a good understanding as to how the solar system itself has sort of evolved.
Yeah, but there's a bit of a data issue, really, the limitations with having enough information to work with. So at the beginning of the exoplanet journey, I was really lucky, actually. When I went to university, one of the professors I had at university, a chap called Mark McCaughrean, he had an amazing career. He worked on the Hubble Space Telescope. Then he lost his job because there was a problem with the Hubble Space Telescope. Then they found out it wasn't his team's fault and they tried to rehire him and he just left because he was so bitter. Anyway, he had this brilliant, fascinating career and he ended up at Exeter. And I'm not sure if he's still there now, but he's at the European Space Agency now. He runs like science missions for the ESA. He used to work on exoplanets, and I just really vividly remember, this was in the early noughties when I was at uni, and he told me about how many exoplanets there were and what kind of systems they were. And you might have heard the phrase hot Jupiter, which I think should be an expression of like excitement. Hot Jupiters. That's a good expression,
Egads.
Yeah, it's like a GADS for the modern astronomy age. Hot Jupiters are a type of exoplanets, which are essentially gas giant worlds like our own Jupiter and Saturn or Uranus and Neptune, but they're so close to their host stars that they're literally roasting. Some of them have cloud top temperatures that are 2 or up to 4,000 degrees centigrade, so really, really hot worlds, and completely inhospitable. Even if they had moons, nothing could live there. Many of them actually orbit the stars in just a matter of days, 3 to 20 days, rather than taking years or months to go around. So these kinds of systems were commonly discovered at the beginning because the method for discovering the systems was either to observe a large number of what we call transits, where the planet goes in front of the star and we see the star's brightness dip a little, which is very difficult to do if you want to find an Earth-like planet, because you're waiting a year between dips. So you have to look for a long time. Or more commonly, it was to look at how the stars wobble, because as the planet goes around the star, the two actually pull on each other. And as the star wobbles, the light coming from the star is actually blue and red shifted. And there's our little culprit, spectroscopy again, that can tell us how the star is moving. Actually, spectroscopy is now so accurate that we can measure the speed of a star moving at a rate of about 1 meter per second, which is about the speed of a person walking down the street, which is kind of extraordinary. So the gas giant worlds pulling on their stars, they were easy to find because they had a huge effect. They were displacing the stars by a measurable amount. So naturally, most of the systems that turned up in the early days were these tightly bound hot Jupiter systems. And this began to skew the narrative about how rare our solar system is. We started to think, well, we're not finding worlds with lots of rocky planets close to the star. But of course, we really didn't have the technology to do that. And it's only recently that missions have actually been developed with a specific focus to do that. Famously, the Kepler Space Telescope, which has now been reassigned to exploring the Kuiper Belt, actually, where Pluto is. And also the TESS mission, the Transiting Exoplanet Survey Satellite, which is operating right now, which is looking at nearby stars. And various other missions are going to work on this in the future. So it's we expect, and the indication from Kepler is good, that terrestrial worlds are actually much more common than we previously thought. In fact, the early releases from Kepler would suggest that even if we were being quite conservative, on average, there should be more rocky, habitable zone worlds than there are stars in the Milky Way. So every star on average has at least one Earth-like planet from the early data. Probably that's, when it all comes out in the wash, it may be a little more or a little less, but probably there are hundreds of billions of worlds similar to the Earth in the Milky Way galaxy alone. So I think I'm optimistic that the solar system is actually not that uncommon. And in the fullness of time, we might learn that the hot Jupiters are actually more uncommon. It's just a matter of what we could find first that has colored our understanding of it initially.
Going off on a tangent here, do astronomers ever see UFOs? Or can you guys identify everything that's out there?
Oh yeah, I know. I get sent so many things. Actually, I get sent so many. When I was at the observatory, I used to get dozens of emails a year of just, I saw a light in the sky, and
Oh, you want to know?
yeah, or they'd send a photo or whatever, and half the time it would be a lens flare, and half the time it wasn't. And so half of them you could dismiss quickly. But the thing about these photos was just the lack of information was staggering. And I don't blame people for not knowing all the information, but I would always ask them, well, when did you take it? Exactly which direction were you facing? What is the scale of the photograph? What is the angular scale? What's the make and model of your camera lens, etc.? Because I was trying to establish what it could be. And a lot of the time it would be like Venus setting after the sun, which, I lived by the sea growing up for most of my young adult life. And by the sea, the planets being sighted over the horizon would often result in people calling the Coast Guard because they thought they'd seen a flare. They'd be like, oh, somebody's fired a distress flare. They'd call the Coast Guard, and then boats would be scrambled, and then, oh, it's just a planet. Nothing to worry about. There you go. That's how the planets affect our lives, if you really want to know. They confuse us. Pilots as well. There was a famous case of a pilot taking an emergency nosedive because he thought Venus was an oncoming plane, which is pretty disturbing for all the passengers at the back. So
yeah, I mean, the pilot sightings always get overpraised because everyone says, "Oh, pilots know what's up there." But
yeah, well, my dad was a pilot. My dad was a pilot
there,
in the Air Force, and he used to talk about UOs, as they call them in the military, unidentified objects, and they're unidentified in the sense that they're not identified. They don't have a squawk signal, which is what all planes above a certain altitude have to have for air traffic collision avoidance and so on. So they could be balloons, they could be birds of a large wingspan, they could be unidentified aircraft that somebody's flying and they don't want to know that they're flying. And nowadays, it's not uncommon for drones to be an issue, because drones are big now. My dad was also a commercial pilot in British Airways, and again, there were a lot of stories about people being confused about things in the sky that they were seeing, interpreting them as UFOs, and oftentimes it was planets, because particularly when you get to the upper thermosphere, really you're still in the atmosphere, but you're kind of high up in the warm part of the atmosphere. The air is so clear, the planets can appear staggeringly bright and bold from an aircraft cockpit window. I mean, they can just be like searchlights in the sky, blazing onto your retinas, which is beautiful to observe. But if you're not a trained stargazer, you might not know that that's what you're seeing, and yeah, it can make you panic. So what was the question? Oh, UFOs. Yeah. So UFOs reports were coming all the time. And
but from astronomers, or just from
but from astronomers, no. But the reason is, yeah, that is the answer, isn't it? But the reason is because things in the sky either move or they don't. And if they don't move, then their positions give away what they are. We have databases for all the things in the sky that have been observed. If something is observed and it's not moving and it's never been seen before, then the first thing an astronomer is going to assume is that they're seeing a nova, which is a star that has brightened so much, maybe 10,000 times, that it's come out of obscurity and become bright enough to be observable. Or a comet, because comets as well travel from the outer solar system. They get close enough to the sun that they start to effervesce their atmospheres, which become highly reflective, and they suddenly become bright enough to be seen. And their comets are just points when they're far enough away. And at this stage, they're moving so slowly relative to the stars that they can appear as fixed objects. But if an object is moving, then its position can be attached to a known object in the Minor Planet database using the coordinates. We can calculate what's in the field. And if it's moving very quickly, it's a satellite. And satellites can be identified quite easily. There's only a few times where I think I've seen or known of a sighting of a satellite which didn't have an identification, and that will have been a US Air Force military satellite usually. There are satellites which are, which we're not supposed to know about, which can be seen.
Anything below that is not your area of expertise. Like if it's like a plastic bag in the wind, that's not
exactly.
That's not going to be for you to consider.
That's for a climatologist or a meteorologist to figure out exactly. That's atmospheric. It's too low to be of interest. Yeah.
Got another question from Michelle. She wants to know about your thoughts about people going to live on Mars. Do you think that's something you might see in your lifetime, or is Elon Musk blowing?
How long am I going to live? I'm drinking a beer, as you say. Is that going to happen in your lifetime? Well, I hope so. I hope to see all sorts of cool things in my lifetime. People living on Mars is a certainty, in my view. There are active plans to put people on Mars in multiple different national agencies right now, not including Elon Musk and his private plans to pursue that. Whether it's like America first or a joint initiative, I think it's more likely to be a multinational initiative. There are big problems to solve to put people on Mars, and anybody who tells you it's going to happen in 10 years is kind of lying about the issues that haven't been solved. I mean, maybe not lying, but they might just be sort of obscuring, because there is a goal to develop investment in sending people to Mars, and you don't really want to tell people that there are certain things that haven't been ironed out. You just want to get their money and then try and iron it out as quickly as possible. So there are a lot of problems with the long duration aspect of
going to Mars is different than like living there forever too. Like visiting once, say, is like one hurdle versus like having like a permanent colony. I don't think anyone's talking about that.
Yeah. So I think in Michelle's question is, are people going to live on Mars? Well, I think maybe another way of phrasing the question: are people going to be born on Mars? To which the answer is almost surely is almost certainly not in our lifetimes, or probably our grandchildren's lifetimes. But it's
the problem is, with what we understand currently of the Martian environment, the only way people are going to live on Mars long term is underground. They won't be living like Matt Damon, growing potatoes in their own poo in a tent, because there's no radiation shielding in a tent. They'll be living underground like rats. I don't think many people are going to want to do that when they understand the full implications. But the problem is, even if not many people want to do it, in a planet with nearly 10 billion people, you can find people who will do things that nobody wants to do. And somebody will be the first person to be born on Mars, probably. the first real Martian. The problem with being born on Mars is it's not good for you. You know, the low gravity, it's not good for your physiological development. And billions of years of evolution, and particularly tens of millions of years of mammalian evolution in our system have ensured that we're extremely well adapted to the gravity on this planet. And so living long-term on another planet is very difficult, extremely difficult.
Question to end on from Michelle, but were you going to say something else before that?
Oh, I was just going to say, for anyone have you seen the Expanse?
Yes.
TV show, book series. It's fabulous. Like, if you like space, go and watch it. It's a really, with one or two very obvious exceptions, it's quite true to how space, like exploration, living in space would work. There's
no anti-gravity or anything like that. Like, it's all based on like real physics.
Yeah, The Expanse is great because it is hard sci-fi for space nerds, and and it presents a kind of dare I say optimistic vision for the idea of exploring the solar system and basically getting off this planet. And I think that the hunger is never going to go away. People are going to want to do it, even if you didn't have billionaires trying to outprove each other on what they could achieve. You'd still have people trying to do it just because it can be done. You just need nations that are kind of rich enough and complacent enough to want to spend money to do something like that. And there is some scientific interest. Well, there's a lot of scientific interest in going to Mars. There might not be a lot of scientific money in sending people there. But what we've learned from the moon is that a single human being working for about 30 minutes can do more work on the surface of Mars than every single rover has done in the past 40 years. So sending people anywhere is really advantageous from a scientific perspective, certainly.
But on the Expanse, though, there is an issue of people being born in low or no gravity, growing up there, not then being able to withstand or live on Earth. They're just not built for it. Their body is just not able to withstand the pressure. And so, if we did extend a colony to Mars, they would not just be Martians, but they'd be Martians only. They'd really, really struggle to return to Earth.
Yeah. I mean, you probably
out of heavier gravities to lighter gravities. You can't.
Yeah, many people here will have experienced a G force of 2 or 3 Gs. When you get to the bottom of a roller coaster and it starts to bottom out, you will experience your own weight pushing down on the chair of the roller coaster. Mars is about 2.5 times less, has 2.5 times less gravity than the Earth. So if you were born there, your body would be adapted for a gravitational force, which would feel 2 to 3 times heavier on Earth when you got here. And so imagine sitting in a roller coaster being crushed into your chair permanently. That's the experience you'd have as a Martian coming to Earth. There's a reason people pass out from extreme G forces. And while you might not pass out, your entire biological system would be under constant pressure. Your heart would be under constant pressure to get the blood around your body, because your blood pressure would be adapted for Mars, and your heart rate would be adapted for that too. So you basically probably would pass out from lack of blood oxygen for being on the Earth too long. We also know that astronauts that have been in microgravity on the space station for a period of over a year or more generally do have a sort of period of difficulty walking properly when they get back to Earth. I mean, part of that is the habit of walking, but another part of it is that the body, the muscle mass emaciates quite a lot in space, and the heart rate slows quite a bit. And so your body has to kind of tune up again for gravity. Gravity's, we take it for granted how invariant it is on the Earth, but even standing on Venus, where the gravity is 90% of the Earth's, would feel odd. Being on Mars would feel very odd, and being on Jupiter, where the gravity at the cloud top's about 3 times the Earth's gravity, would be, super uncomfortable to try and stay there.
Does anyone else have any other questions? If not, I thought the one from Michelle is a great one to end on, which is, I think the question is partly about you and kind of your personal goals with respect to astronomy and science communication. But I think more generally, what are the goals of an astronomer? Like, is it all just about discovering new stars? What does an astronomer wake up in the day up and want to do with their day?
Oh, it's a really good question. I do think it's important to point out that astronomy is a huge field, and really it's an umbrella term for so many interesting sciences. So you've got astrophysics, which is what I did. Astrochemistry is a very interesting field. Astrobiology is a young but interesting field. cosmology is the study of the whole universe and how it and its large scale structure and its future on epic time scales. And then you've got things like planetary science and astronautics, astronautical engineering. There are just so many fields in astronomy. It's hard to say, but I think that if you dream about really, really big mysteries, then astronomy is a very difficult thing to put out of your mind, because everybody who thinks about whether there's life on other worlds or what exactly happened around the time of the Big Bang, or whether there was something before that and how we can contextualize that concept. Anybody who's interested in those questions knows that it's astronomers that are working on them and have to work on them. But when you actually get down to astronomy, when you actually get into doing like the day-to-day, you might find that you just want to learn about what young stars do in their lives. And that might be a very specific kind of observation. You might be on a mountaintop or a volcano top in Hawaii using an infrared telescope to look at stars in a nebula. And the lives and the affairs of those baby stars that are a few tens of thousands of years old can become so fascinating. You can spend your entire career just working on that. I think there's just so many questions to answer. There is like something for everyone, whether it's an individual world or a class of worlds or a class of stars or exotic objects. It's hard to say, but if you like solving mysteries, astronomy is a good one, because there's just there's a huge gulf in our understanding of what's really happening. For that very reason we talked about, not being able to go places and take samples means that we have to take the light and put the light into our simulations and hope that our simulations are good enough to tell us what's happening. And that makes it really exciting, because there is lots of stuff that hasn't yet to be found.
That's amazing.
Hot Jupiters.
Hot Jupiters.
Hot Jupiters, exactly. Hot Neptunes. There's, there might be cold Mercuries. Who knows? The possibilities are literally endless.
It's really great. So, I mean, thank you so much for coming. Thank you for the questions. Brilliant. It's been really great. Andrew, what are we doing in 2 weeks?
Oh, I think Chris might be better answering that.
So, yes, and I've got a question for Tom about this, actually. So, so in 2 weeks, it's round about Halloween, and I wanted to look at some of the more unusual explanations for ghost sightings. And during my research, I found there is apparently a correlation between aurora activity and reported ghost sightings. I couldn't find this mentioned in the definitive guide to auroras. Is that something you're going to put in the second edition? Or
yeah, you're the first person to introduce that concept to me. That's fascinating. Let's talk about that. I'm curious.
So, have
we
you
get a spoiler for 2 weeks from now?
Yeah, give us a. What's the spoiler, go on?
So the theory is that the magnetic activity that causes auroras could short circuit the temporal lodes in the brain and cause you to hallucinate other entities.
I mean, from my perspective, that as somebody that is not an aurora scientist or anything like that, but just had to spend a year reading about all the science and so on, I can't think of a way that heightened magnetic activity from what we call geomagnetic activity, which is really what auroras come about as a result of, it doesn't really permeate into our bodies in a meaningful way. That it just doesn't interact with our bodies in a meaningful way, which is not to say there aren't interesting things that happen close to the ground, which could be connected with ghost hauntings, I suppose, one of which would be the aurora noise phenomenon, where something like 70 meters above the ground, you can get a static buildup in what's called an atmospheric inversion layer, and the snapping and rustling and crackling has been widely reported as the aurora speaking to people and making sounds throughout history. That's one proposed explanation, quite a good explanation for how aurora noise forms. So even though the northern lights are 100 miles above your head, 70 meters above you, the air is charged by that activity. But that snapping and crackling sound is occurring because of the buildup of static charge in the air, and static charge doesn't permeate into the human body. It's something that you can get on the surface of your skin, but it's not going to electrify your brain, your lobes in your brain. As far as I know, I mean, I'm not a brain scientist, so I couldn't say for sure. That's a curious one. Yeah, I know that, magnetic activity can slightly scramble the navigational skills of certain types of migratory birds, but I don't know that it has an effect on humans. And I think that would be easy to prove.
Yeah.
It would be easy to induce hallucinations using magnetic fields in a human being in a
Well, that's
field
what
test.
Persinger has been doing with his God helmet. So that's something we'll
The
be
God
looking at.
helmet.
Yeah.
Cool. I need
Something
a
we'll
God
be
helmet.
looking at next week.
Okay. Spoiler for me. Is the God helmet working for Persinger, or is it maybe a little bit suspect?
It works perfectly for Persinger.
Okay. But maybe not for the scientific community. Okay.
Replication's been a problem.
Yeah.
Okay.
Exactly.
The central problem, isn't it? Yeah. Okay. That's very interesting. I like that a lot. Maybe there is a second edition coming about ghost sightings. And if there is a correlation between auroral activity, which we can historically look up at any time, and a spike in reported ghost sightings, that is in of itself interesting. But what would be more interesting is if there's any geographic connection, because while geomagnetic activity can be significant during the aurora displays, it doesn't necessarily go far south enough to be a problem or influential at most populous latitudes. So unless these ghost sightings are all taking place in the Arctic, if there was a correlation where the ghost sightings kind of were very prominent in the Arctic, a little bit less prominent in Northern Europe, a few in Greece, but nobody near the equator is really having them, then that would be an interesting data point to work with.
Cool. Well, to find out more about ghosts and maybe auroras, to come join us in 2 weeks' time. And for now, thanks so much for joining. We will see you next time. Buy his book.
Yes.